Okay, now we're going to go through the solutions for the F2 reflections, where here are the lessons where it talks about coefficient of variation and validity of the linear regression model, and that goes with the notes. We're probably going to need Snaplet today because we got some data. So what I'm going to do is go ahead and open a tab for Snaplet. All right, and here's our data. So let's first look at this. From experience, Japanese cherry trees tend to blossom early when spring weather is warm and later when spring weather is cool. Here's some data on the average March temperature Celsius and the day in April when the first cherry blossom appeared. Use this data for parts A through E. So what I'm going to do is I'm going to pull this aside so I can look at the data and type it into my Snaplet. So what we're dealing with here is two quantitative variables. Remember, bivariate data, and it's quantitative. So our first one is Celsius, the temperature. This explains how many days it takes for the first blossom. So you can just type the data in with either a space or a comma between them. And sorry, it would have been nice to have this with a copy paste. Oops. And then the day. And that should be right. Hopefully there are no typos in there. There you go. There's the data. So describe the strength and describe the strength of the correlation. So you will, this is the first question they ask, right? And if you look at the data right here, you can see that it's definitely negative, all right? The question is how strong it is. Well, since I have put the data in Snaplet, actually, I can come here and get a really good idea. It's a negative 0.85. So believe it or not, let me go ahead and show you the regression line. The dots are not that far away from the line. And an R of negative 0.8486, that's pretty close to -1. So we actually consider that strong. So we're going to say it's strong and negative. Now, a blank of the variability in the amount of days till the first bloom in April is explained by the linear regression model using the average March temperature. So what percent of the variability in this graph, so what percent of this variation right here about the of these values is explained by this line? Why is this one so low and that one's so high? Well, because the line predicts it'll be close to that low and close to that high. So how do we figure out that value? Well, if you make sure to calculate your regression line, it's going to go ahead and square the R for you. This is R squared, and that explains percent of variation. But make sure to change that to a percent by moving the decimal 2 places to the right. So we'll go ahead and do that. And it's a 72%. So it's not 0.72%, it's 72%. Which of the following statements is true using the regression line from the data? So it looks like we're looking at our slope. So if we got to go to our equation for our regression line, right? And our slope, that's not the slope, that's the y-intercept. The slope is negative, and it's in front of x, okay? So it's about negative 4.44. So we're going to look at our options. We expect a decrease, not an increase. There's a 4.44, all right? And it has to be a decrease. So there you go. That's the correct answer on that one. If the temperature is 4 degrees Celsius and the first bloom occurred on the 21st day of April, interpret the residual for this day. Okay, so if the temperature is 4 degrees Celsius, what we're going to have to do is actually take this equation, all right? Let me go ahead and just pull up a blank Cami for you. So give me a second. I got to go blank page. That's fine. All right, so the equation is, let me just take a snapshot of the equation here so I can have it for my reference. It's on my Snaplet. It's not on my WebAssign. Okay. So I'm going to take a quick picture of my equation so I can reference it. Okay. And we'll put it in my stafflet. Oh, there it is. All right. And they said, what's the question saying? When the temperature is 4 and the actual first bloom occurred on the 21st. So what that's telling us is that X is 4 and Y is 21, not Y hat. So the question is, what would Y hat be? So what we're going to do is calculate, I'll say 32.07 minus 4.44 times the X value, which is 4. So I'll need Google to help me with this a little bit, since I don't have my, I guess I could pull up a calculator. I should be able to put this in Google. And I'm getting 14.31. All right. So, all right. So let's go back and look at our choices. Oh, so that's the predicted. So I'm not done yet. Okay. Oh, what happened? There we go. There we go. Why'd that all go black? That's so weird. Maybe I should refresh it. Sorry, guys. Technology. There it is. All right. So that's the predicted, but the actual is 21. So residual equals actual minus predicted. So the actual is 21, and then minus 14.31. All right. So that's about, let me go back. Let's just say 21 minus that. Sometimes I'll do it backwards and just remember that my sign is, so it's positive. I did it backwards, so it's positive. 6.69. Okay, so that is my residual right there. And going back to the question, now which one is higher? The actual is higher. So did I overpredict or underpredict? I underpredicted. My prediction is low. So let's go ahead and go to our prediction. And if the temperature, so we underpredicted, and it was closer to this value, because we said 6.69 is probably a rounding issue, by 6.75 days. Okay, let's go ahead and hit submit. We'll come back because we got a lot. We're almost done with this, by the way. It's just, there we go. So going through, everything looking good. Yes, we are all correct. Okay, on to part 8. Is a linear model appropriate for this data? So we'll go back to our stafflet. Oh, that's my gradebook. That's not my stafflet. Luckily, it didn't have anything on it. So let's go back to our stafflet and look at the pattern in the residuals. Now, there are a couple ways. You can kind of look through the thing and say, is it kind of curvy? But this is really the plot that you want to look at. The pattern in the residuals. I don't really see a lot of major variation going on. So, I mean, it's regular variation. There's no pattern in here. And so if there's no pattern, we're good. We're golden. So we're going to say yes, because there is no pattern in the residuals. A positive value for a correlation indicates that your slope is positive. So as increases in X tend to be accompanied by increases in Y. So this is a general. The numerical value for a correlation can never be less than -1. Correlation is anywhere between 1 and -1. Let's see. For it can never be less, can be greater, no. Can never be greater than 1. That's true too. Hold on. That's interesting. I wonder why. Okay, so I guess this is trying to get them both. So technically it can never be less than 1. It can never be greater than 1, but it can never be greater than 1 and can never. So both of these, okay? I guess it could have formatted that differently. A Pearson correlation of R is positive 0.85 indicates that the graph of the data would show just pretty much the points are going to be kind of close around the line, so it's not widely scattered, and it's a positive slope. So that's what we're going to say here. And then finally here we have one more practice. So let me go ahead and submit these other two, and we'll do this last extra where I'm going to have to do a stafflet again. Let's see, do we have them all? Yes, they are all correct. Ooh, lots of points towards the end here then. For the set of data, calculate the Pearson coefficient. So I'm going to go pull this to the side again so I can see it. And we're going to go to, not there, there. Oops. Mrs. Overman's having a day. Good thing I don't have anything sensitive open. Okay, there we go. So here I'm just going to put x, 1, 2, 3, 4, 5, y, 9, 7, 4, 2, negative 3. Begin analysis. And they want the Pearson correlation coefficient. So basically, there it is, negative 0.983. Now, if I calculate the least squares regression model, then you also get r squared. And the reason I have that is I always keep thinking the Pearson is the r squared. So give me a second. So we had negative 0.689. That is the correlation coefficient. The coefficient of variation is actually, So when you see the word Pearson, I'm going to say, really, this is the coefficient of variation. I might go and add those words. So this is why we wanted the squared value, not the other. So go ahead and submit that answer, and it will be correct. I had a feeling, I was like, oh, the wording's off. But whoa, oh my. Hold on, let's go look. It's got to be, Mrs. Overman's freaking out. Did I have a typo? No, I'm getting the right values. Negative 0.984. Oh, negative 0.9. It is the R. Okay, it is the R. It's just I clicked on the positive instead of the negative. Silly Mrs. Overman. Silly Mrs. Overman. There you go. So this is the Pearson correlation coefficient, not the coefficient of variation. And we're all good. And then please, and then please share here either one thing you struggled with. Maybe you did the same thing Mrs. Overman did, and you're like, oh, I couldn't keep track my R or R squared. And you learn that the Pearson correlation coefficient is just the R. It's not the R squared.